Alright, the reason why I made last time's video an AMC walkthrough is because I have to practice for math competitions. And guess what? I still have to practice for math competitions. Like, what the heck? How is that even possible? What? Dude, literally BMT is coming up on October 3rd and 4th, and I have not done math since Eon. I mean, to be fair, I did it like this week, but like, you get what I'm saying. And because I just love getting destroyed, I put my first choice for the focus test as calculus, even though the only calculus I've ever done is AP Calc in 10th grade. God dang. Kinda not a very big brain move, but like, I want to learn Calc. Calc seems like the cool area of math, honestly speaking. But I don't know where I should practice, so if you guys know where I should practice it, let me know. I need some Calc problems. Hello everybody, I'm Kara, and today, notably, we are not practicing Calc because I'm a troll. We are actually going to be practicing AMC where we left off, okay? So we got the same deal. We are going to start with problem 18. We are going to go as far as we can in 30 minutes, and it's probably not going to be very far because on the actual test, I got demolished, so very unlikely that we are going to solve many of these. Alright, let's get this party started. 30 minutes on the clock, and we are in. Okay, 18, quadrilateral ABC satisfies the 90 degrees, so AB and AC are, wait, what? ABC and AC, oh, fancy. Okay, I see how it is, and this is 90 to 90, and we got AC, oh my god, this is so annoying, holy. So this is 20, this is 30, okay, and then we got, that is a straight line, and then AC and BD intersect at point E, and AE is 5. Oh my god. So to scale, holy moly. Whoops the daisy. Okay. Now we're actually gonna do, what the heck? Okay, so we know there's a 20-30, okay, and then a 90-degree angle, okay. Alright, so now we want the AE to be 5, so that's like right here, which means that this is kind of like that. Nope. Okay, whatever. A, B, C, D. Alright, and then this right here is that. Okay, and this is E. Alright, now what? They're not even a cyclic quadrilateral, so I can't inscribe it in a circle and use power of a point. God dang it. 20 is this length right here, right? Okay, so we know what this length is then, right? So 20 squared plus 30 squared at 4 plus 9 is root 10 root 3 at 10 root 13, okay? And that means nothing. Okay, well, what do we know? Well, what could we possibly tell from this nonsense? So, we know, okay, well, I mean, we know stuff because this is 5, so that means this is 15, right? And that means that we know this length right here. Well, basically, we want to find where it goes. Oh, so this is the diameter of a circle. And then we have this line, and we want to see where it intersects the circle. Oh, wait, that's big brain. Okay. So, we basically have, like, this right triangle, right, like this, and we got a line 5 right here, and we know the slope of this line, right? It basically is, it goes up 30 and left 20, so it's like -3/2, right? And its y-intercept is here, and we want to see where, okay, well, this is 15 technically, okay, so -2 is what it is. And we want to see where it intersects the circle with diameter 20 centered at here. Okay, so let's see. So the circle is just going to be x minus 10 squared plus y squared is equal to radius squared, which is 100, and then the equation of the line is going to be y y is equal to -2 times x minus 5. There we go. Okay, now we're getting into business. -2 plus 10. Okay, so now we basically got to plug in stuff and try to find out a solution. So we could probably just plug in for y and we will be Gucci, yeah. So basically we get like x squared minus 20x plus 100 is equal to like 4x squared minus 40x plus 100. Wait, plus here, and then that is equal to 100. So essentially, we got 5x squared minus 60x plus 100 equals 0. And then if we divide by 5, we get x squared minus 12x plus 20 is equal to 0, which means we get, what do we get? X minus 10 times x minus 2. So x minus 10 is probably like the other intersection, right? Like it intersects once on this side and it intersects once on the other side. So I mean this must be x is 2, okay? So now that we know that x is 2, then we basically know what, well, we know that this length over here is 3, and then the slope over here is 2, so this is going to be 6. So the height of this triangle is 6, the base is 20, which means that the area of the triangle is just 60, which means that our total area, holy moly, this is getting kind of big brain, our total area is 60 plus 20 times 30 over 2, which basically is equal to 60 plus 300, which is 360, which is D. Oh my god, let's go! Alright, in the actual competition, I never feel comfortable coordinate bashing, but honestly, it's not even that bad. I should be a little bit more open. We gotta be accepting of chord bashing, okay? Just because it's different, just because it's nasty, doesn't mean we have to judge it for its looks, okay? Alright, problem 19. There exists a unique, strictly increasing sequence of non-negative integers such that this nonsense is true. Okay? How the heck do you do that nonsense? Well, I mean, it's basically like 2 to the 289 minus 1 plus 2, right? Technically? Does that even help? I mean, then we could basically just say it's 2 to the 17 minus 1 plus 2 over 2 to the 17 plus 1, which is basically like a geometric series, right? I'm not being trolly-poly. Wait, no, it's an odd number. Oh, it's not a, I'm trolling. This is not how a difference of squares works. Okay, hold up. Nope, no, hold up. Pretend that didn't happen. Okay, so basically, I think it's like, you could use the, what is it called? Could you use like the 2 to the, or like, x cubed is whatever. Hold up. Well, so it would be like 2 plus 1. Or yeah, 2 plus 1 times 2 to the like 288 minus 2 to the 287 plus 2 to the 286 and so on and so forth. That would work, right? Yeah. And then same thing in the denominator, you basically have 2 to the 16 minus 2 to the 15 plus dot 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 minus dot 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 whatever. Okay. Does that help? And then this would cancel out. But then you're left with even more nasty thing, which is not good. Although, it is just a geometric series, and we know how to represent geometric series in terms of stuff. So if we have a geometric series, why don't we just do that, right? Yeah, so, no. So then it's just gonna be like, it's just gonna be the same thing. Yeah, so this is like basically going backwards for the geometric series thing, but then if we do anything else, then somehow we need to get rid of the denominator. Wait, can we do the same like strategy, right? Like, so you basically have 2 to the 17 plus 1 times 2 to the 17, right? Oh wait, we could just logic it out, right? So 2 to the 2 to the 289 minus 17. So it would be 2 to the, I can't subtract. Why is subtracting so hard? God dang it. Okay. And then, like, that would give you a plus 272, so then you do minus 272 minus 17 is what? Oh, I can't subtract for my life. Okay, 55, and then 255, and then plus 2 to the non-negative integers, though? Non-negative integers, hold up. I mean, okay, well, let's just do this for now, right? So then it's like 2, 40, 30, 38 minus dot 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 dot, all the way to like, so what would the last one be? So you would eventually get to like, would it be plus 17 or minus 17? So if you subtract 17 an odd number of times, it'll be positive, and if you subtract 17 an even number of times, it'll be negative. So the 1 at the end is going to be negative because you're subtracting 16, 7, no. You're subtracting 17, which means that it should be, it should be positive, okay. So positive at the end, and then minus like 2 to the 17. And does that cancel out? So you basically have minus 2 to the 17 times 2 to the 17 plus 2 to the 17 minus, or plus 2 to the 17 plus 1. And then yeah, you just want the plus 1. So this works, okay. So now we basically have that we want to find 2 to the 272 minus 2 to the 255 plus 2 to the 238 dot 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 minus 2 to the 17 plus 1, that this is equal to some strictly increasing sequence of non-negative integers. Strictly increasing. So can we factor things out? No, but then it wouldn't be a power of 2. Or could we? So it has to be a bunch of powers of 2. What do you do with all the negative powers of 2 though? That is the question. Okay. So basically, you get like 2 to the 255 times 2 to the 17 minus 1, right? And then 2 to the 17 minus 1 can be represented as like, um, it can be represented as a sum of, it could be represented in binary, right? Like, what would it be specifically? Um, it would be like, hold up. So basically, wait. Yeah, so if A is equal to 1 and R is equal to 2 and N is 17, then you basically get this. So it basically does 1 plus 2 plus 3 all the way to 2 to the 16, which works extremely well. Oh wait, no, sorry. No, not this. What's going on? Okay, 1 plus 2 plus 2 squared plus dot 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 2 to the 16. Okay, right? And then basically, wait, this works so perfectly, right? Because then it's basically 2 to the 271 plus 2 to the 270 plus 2 to the 270, 2 to the 269, hey, very nice. Okay, so basically, and then it goes all the way down to 2 to the 255, and then same thing, it'll go from 230 to the 238 all the way to 2 to the 254. So it basically has all the numbers less than this, right? All the way up till 0. Wait, that doesn't make sense though, right? Oh, but then there's the extra 1 at the very end? Well, okay, so, hold up. So then it goes to like 2 to the 17, all the way down to 2 to the 17, and then you got 1 just hanging out there, that beautiful 1. So what does that do? So you basically have the number of stuff here. Wait, but there's nothing even close to that, right? Strictly increasing sequence of non-negative integers. So this would be plus 2 to the 0. But then that's not even an option, right? Like, 2 to the... Okay, this is a equals 1, r equals 2, and n equals 17, right? This is right. There's like breaks in it. So it's not 2 to the 2. Oh, okay, so the next thing would be this... It'll go to 2 to the 37, so 2 to the 237. And then all the way down to 38 minus 17, which is 21. Okay, so we basically have some gaps in here, so now we can actually calculate it. So, how many numbers are there here? So, you basically have like 17 through 272, which is basically 16 numbers, right? So, 8 of those, 8 pairs, right? We want to pair them up. So, 8 pairs, and each pair has 17 numbers, 17 terms, so 8 times 17. And then we got this additional 1 at the end, so it should be that, which gives us 80 plus 56, which is 136 plus 1 is 137. Epic. See, good stuff. Holy moly, this is epic. Let's go. We have yet to drop a question. No, no, this is like musical lunch problem. God dang. How's our time even doing? Oh, 15 questions. That's not great, but it's okay. Okay, so you basically have 0, 0, right? You got your 4, 0, and then you got your 0, 3, alright. And you consider a bunch of rigid transformations. Oh shoot, I don't like these. Okay, let's see. So, you got that. How many will the 125 sequences of 3 of these transformations will return? Oh, so it's only 3. Okay, there's 125. Oh, okay, we could literally just brute force it, right? Wait, straight up we could, right? Like, there's not even that many. If we could find 21, then we know it's E. Okay. Well, let's not get too ahead of ourselves. Let's think about this. So if you rotated, is it around the origin, right? Yeah. So basically you rotated anything around the origin. If you reflect it, so you can either, reflect against the, okay, so if you do a reflection, as long as you do 2 reflections, you're chilling, and then you gotta rotate it. Well, okay, think about it this way, right? Like, if you rotate it, like you can rotate it however the heck you want for the first 4 times, right? But then on the 5th time, you have to rotate it back to what it originally was, right? So basically, we could have 3 cubed, right? It doesn't matter what the first 3 are, as long as they're rotations, we're chilling. Or 3 to the 4, right? And then the 5th one we know is like fixed, right? There's only 1 rotation that'll bring it back to the original point. All rotations. Now, what happens if we do 1 reflection? Then if we do 1 reflection against the y-axis, then there's no way to rotate it back to its original position, so that doesn't work. But what happens if we do 1, why don't we do 1 y-axis, same thing, or x-axis? Let's see. If we do 2 x-axes, it works, right? If we do 2 y-axes, it works. If we do x and a y, then you can just rotate it 180 degrees, and that's fine. So essentially, we could do 2 squared, right? Any 2 reflections are fine. Wait, this doesn't even make sense. What? 3 to the 4 is already way too big. Hold up. Oh, 3 of these. 3 of them. Okay. So it's just 3 squared. Wait, that makes it so much easier. So 3 squared. And then the other option is we do 2 reflections and then 1 rotation to bring it back to normal, so times 3. Or no, the rotation we gotta do is fixed. And basically we can do 3 choose 2, right? It depends where you want to do the reflections, that also matters. Oh, well, this is also 3 choose 2. Oh shoot, that is the complicated part. So this part is for sure right? Like you can choose where the heck you want to do the reflections and in which order, it doesn't really matter. But for this one, it's kind of weird. Because sometimes you do... Okay, so this is just 4 times 3 is 12, so we eliminate A. And now this one, it's at least more than 12 plus 9. Wait, what? So it's just 25, right? Because, like, the minimum is if you do any rotation, combination of rotations for the first 2, and then you fix the last one. But the thing is, like, you could also do it in a different order. Wait, oh, is this right? Hold up. So you can do any rotation first, you can do any rotation second, and then you'll guaranteed get a unique rotation. Yeah. Is that not right? Yeah, this should be fine. But 21 is not an option, so I'm clearly doing... my thought process is kind of wrong. Okay, so if you do like a 90, 90, 180, right? That works, right? And it's not over counting that. Okay, so what does it count in 3 squared? It counts 90, 90, 180, it counts 90, 180, 90, it counts, well, there's so many. Okay, well, fine, let's 90, 270. Is 0 an option though? Oh, 0 is not an option though, I see. Cannot, if you get back to the original place, in the first 2, then you're screwed. Okay, so essentially that means that this gets roasted completely, right? Because you can't do 2 x reflections, because then you have to do a 0 degree rotation, which doesn't make sense. You can't do 2 y's, but you could do an x and a y, and there's 2 ways to do that. Either order works, and then you just do 3 choose 2, and you got to do a 180 there. So this one is just 6, right? And then for this one, it's kind of different, because if you do a 90, 270, it brings you exactly back to where you were. If you do a 180, 180, it takes you exactly back to where you were. Are there any other options that take you exactly back to where you were? So if you do a 90, it has to be a 270 to take you back. So that's 2 options that get demolished, so minus, voice crack. So 3 squared minus 2. And then we also have to subtract the option where it's 180, 180. Anything else? Any other invalid ones? Are there any? No, that seems right. So 6 plus 6, so 12. Oh, it is 12? Wait, seriously? Am I trolling? I'm pretty sure it should be 12. I don't see why it would not be 12. I'm pretty sure I thought of all the cases, right? So if you choose the first 2, whatever order it is, like each one of these orders are distinct, and then the last one's fixed, so that's fine. For reflection, you choose which reflection you're going to do. Well, you have to do a x and a y at some point, and then you could choose which order they are in, and you also choose which spot they're in, and then the remainder one has to be a 180 degree rotation. So yeah, I think 12 is the answer. Hey, let's go! Oh my god, we are on a roll, let's go. Alright, we probably can only do one more, really? Okay, well that's kind of sad, but it's alright. Okay, how many positive integers n are there such that n is a multiple of 5 and that the least common multiple of 5 factorial and n equals 5 times the greatest common divisor of 10 factorial and n? So least common multiple equals 5 times the greatest common divisor. Okay, so basically the equation we have is that LCM of 5 factorial comma n is equal to 5 times GCD. Let's write this neater. LCM of 5 factorial and n is equal to 5 times the GCD of 10 factorial and n. Okay, so essentially, what does that help us with anything? So we know, well basically we know that n is a multiple of 5, which means that like it's basically the same thing as saying 5 times the LCM of 4 factorial and n over 5? Yeah, 4 factorial and n over 5. And then if it's divisible 5 here, it's the same thing as 2 times 9 factorial, comma n over 5, and then this is 25. Well, we could take this out, this goes to 5, okay. Now, how do we make sure that this is true? So, your GCD has to be a subset of 9 factorial, right? So, it has to be sum of those factors, and then multiplied by 5 is going to be LCM of 4 factorial and n over 5. But basically, your 4 factorial times n over 5 over GCD of 4 factorial, comma n over 5, right? So the more common thing we have with 4 factorial means the smaller our LCM is going to be. So we had to balance that out. But there could be a lot of these n. I don't see how we could relate it though. Hold up. Well, now we have like 2 similar things though, right? We have 4 factorial over here, and then we have a GCD on both sides involving n over 5. So essentially we got like 4 factorial times n over 25 is equal to GCD of 2 times 9 factorial comma n over 5. So does that mean that n has to be divisible by 25? Hold up. Oh yeah, basically it does. It does have to be divisible by 25, okay. Wait, does it? Does that even make sense? Logically, yeah, it does, okay. Makes sense. No? What? Hold up. No. Wait, what? Times GCD of 4 factorial times n over 5. Okay, let's just... Okay. When the timer stops, we are gonna try solving this. I don't think I could though. This seems hard. Okay, hold up. Okay, let's say that n is not divisible by 25, right? Then our least common multiple will be a multiple of 5, but the GCD will be a multiple of 5, and not the LCM, but hold up. But if it's divisible by 25, then the right side is gonna be divisible by 125, and the left side is gonna be not... Wait, wouldn't the right side always just be 5 times more? Oh. So basically you get stuck at 2 on the right side. So you need at least n is 125. So n has to be divisible by 125. I forgot the notation. 125 divides n, okay. But does that always apply? So you need 125. Okay, so this will basically be like 5. Let's say that n is equal to 125k. That basically means that this is going to be 5k, so 5 factorial k, and then this is going to be 25k, and it's going to be 25k. So the GCD, the 25 doesn't contribute to the GCD because we know that this is not divisible by 5, same here, or actually it is. So our GCD will at least be 5, right? So we'll take out a 5 from here, and then this will be like 9 times 8 times 7 times 6 times 4 times 3 times 2. Okay, so essentially what we have now is we have 5 factorial k is equal to 5 times 9 times 8 times 7 times 6 times... Oh, that's not what we're doing. Hold up. 5 times GCD of 9 times 8 times 7 times 6 times 4 times 3 times 2 times 2 comma 5k. And then the 5 doesn't matter anymore, so that goes out. And times the GCD of 4 factorial times k. But we know that there's literally a 4 factorial right hidden in here, right? So it'll basically just be this squared, right? And then we can get rid of this. Oh, the timer's out, but I think we're close. Let's attempt it, okay? We'll attempt it for like 5 more minutes. Let's see. Wait, there's another 4 factorial in here, so then it'll be this cubed, right? Because then, oh wait, that's not how it works. Hold up. 9 times 8 times 7 times 6 times 5, whoops, times 4 times 3 times 2 times 2, comma k. Okay. Well, okay, so k is equal to 4 factorial. K equals 4 factorial times 125 works, okay. But what else could it be? So if we make it divide by 2, then the GCD here would just be k. Well, any factor of 4 factorial would work too, I think. No. Huh. Wait, yeah. Wait, no. No. So other factors don't work. Technically, this would be this, and then that's 4 factorial right there. Oh, but you could take any multiple of this, and then multiply it by 4 factorial, and then it would work, right? Because then you'd have 4 factorial, and then so this one would be 4 factorial, and then this one would be k. Oh, okay, so it's basically just the number of factors of this thing. So that would be 2 to the 1, 2, 3, 4, 5. So 2 to the 5 times 3 squared, 3 cubed actually, times 7. So that is 6 times 4, 24 times 2 is 48. So D is the answer, let's go. I think, hopefully, it better be. Yes, let's go. Holy moly, we did it, let's go. Did not expect that, what the heck. Alright, we actually solved it. That's pretty insane, not gonna lie. Thank you guys so much for watching. I hope it was helpful. I actually kind of like doing math again. I don't know why I stopped. It's kind of addicting. Honestly, I probably won't have that much time to do this much math, but like, you know, we could do it for you guys, and then you guys motivate me to do it, so it's epic. Perfect. Also, what the heck? Why are we at 1400 already? That should be illegal. But whatever. Thank you guys so much. But anyway, I'm getting off track. Thank you guys so much for watching again, and see you guys next time.